organizers for this very special invitation. The last time I was at the Arizona Winter School was in 2007, and it was the final year of my graduate school. And it was a very difficult time for me because my postdoc situation was very, very grim. It was already mid-March, and I was grappling with the decision of whether to leave mathematics. And at the end of the week I had here at the Arizona Winter School, I decided that it was not yet time for me to leave this wonderful community. So I made, I think, the right decision, and now here we are. So very, very special and very meaningful for me to be here. Okay. So my lectures are called Modular. Oh, perfect. Thank you, thank you. Modular. Oh, good. Curves at, how does that look? Okay. At infinite level. And the title is supposed to invoke the following scenario. So we've got these modular curves. I don't really care about the cusps from my point of view. And they form this kind of inverse system. Each one maps down to the last. And for now, you can just think of them as Riemann surfaces or even just as topological manifolds. And something like a modular curve at infinite level would be something like this thing. Y of p to the infinity would be like an inverse limit of y of p to the n's, where n is at least 1. That is, a point of this thing would be a compatible system of points of the corresponding modular curves at the finite levels. And this is a very strange thing to be doing, even just from the point of topological spaces. And just to give you a little analog that's a little bit simpler, let's do the following thing. We all know what S1 is. It's a manifold of dimension 1. It's even a group. It's a topological group. But I'm going to do the following weird thing to it. I'm going to take the inverse limit along the following map. X goes to x to the p. I'm very fond of doing that nowadays. So x goes to x to the p is this map from S1 to S1, and S1 wraps around itself p times. So somehow it's the limit of the following process. The first step is this, and the second step is like coils around itself, and then the third step is like coils around itself, like p squared times. And somehow this topological space is the inverse, the limit of this process. It's something infinitely coiled about itself. And the topologists refer to this thing as a solenoid. And I'm going to leave it to you to verify that this is a very pathological sort of space. So for instance, it's connected, but it is not path connected. You can't get from one point to any other point via a path because there's infinite looping to get through before you get there. It's like the topologist sine curve, but it has the virtue of also being a group, so it's got this nice group structure to it. One other important thing to observe, that it's not just a group. Somehow when we took this inverse limit, the thing became a z1 over p module. So it became legal to divide by p in the inverse limit, whereas S1 you can't divide by p, it's ambiguous. Taking that inverse limit resolves the ambiguity of dividing by p. And then the final thing I have to say about this space, and then I'll never talk about it again, is that you actually have a nice presentation for it. Here it is. This thing is isomorphic to, as a topological group, R cross ZP, the p-adic numbers, modulo a diagonally embedded copy of Z. Okay, you can work that out. Not hard at all. But you have this nice presentation, and the thing surjects onto the group ZP modulo Z. I mean, that group just makes my head hurt. It's ZP modulo a dense, not closed subgroup. The thing is horribly not Hausdorff, right? So the thing is just really weird and pathological, and I like it. So here he goes. I'm going to put it over here. All right. So and now, but that's a topological space, and we're not topologists. We're number theorists. So I want to do a p-adic analog of that analog. So this is all in the name of motivation. So this is a p-adic analog. What I'd like to do is consider the following thing. Let's consider the ring of power series over ZP. ZP double brackets T, right? And I think geometrically. So I think of this thing as something like a disk. So I'm going to write down this funny thing, SPF. I don't want to take spec of that ring because that's a topological ring, and I want to do some kind of construction that takes care of the topology. And that thing is the formal scheme, the formal spectrum of ZP double brackets T. If you've never seen that construction, don't worry about it. I just want you to think of this as the p-adic formal unit disk. And the reason I think of it that way is that a power series with p-adic coefficients converges on the open unit disk, and I forgot to include the word open, and I really should. Okay. So, great. I want to do the same thing with the disk that I did with the circle on the last slide. So I do this thing. I take this inverse limit x goes to x to the p of d. All right. That thing is a formal scheme. It's an affine formal scheme. So it's spoof of something, and that something is a local ring, which I'm going to write as zp double brackets t to the power of 1 over p infinity, and that is going to be the kind of the star of the show. So this ring, I have to define it for you. So I'm going to, so this is the inverse limit, corresponds to a forward limit of rings, and those rings are, well, here, on the one hand, the thing that I started with, zpt, maps to zp t 1 over p. So this is just power series in a variable I'm calling t 1 over p, and t goes to the pth power of that variable, and so on and so forth. And somehow this inverse limit should correspond to the forward limit of these rings. So I should take the union of these rings. But when I take the union of those rings, the result is not complete. You see, when in the union of these rings, I could try to write down some power series like t plus t to the 1 over p plus p squared t to the 1 over p squared, and hope that the thing converges, but that thing does not converge in the limit, in the union of those rings, because it doesn't belong to any of those rings, because it involves arbitrary pth roots of the variable t. But we still want it to converge. I mean, it looks like it's converging p-adically. So what I have to do is define this thing as the completion of something. I want it to be the completion of the union of those rings with respect to the ideal, well, whatever the maximal ideal of the first one is. So that maximal ideal was p comma t, right? That's the maximal ideal of this local ring. And I get something huge, really huge. Contains power series like this, and it's also not noetherian. So we've kind of moved into a non-noetherian ring, and it's a kind of Faustian bargain. We give up noetherianness, but in exchange we get a lot of very cool and very interesting phenomena. So namely, I'm going to show you, So I'd like to demonstrate for you something that happens in this ring. I'm going to give you a fractional power series, f of t, inside of this ring with the following properties. So first of all, its constant term will be 1. And second of all, when I take f of t to the power of p, the exponent goes in like that, even though we're in characteristic 0, okay? And I don't mean for this thing to be constant. Obviously f equals 1 would do the trick, but I don't mean that. So something like this exists in this ring, but it does not exist at any in any noetherian power series ring, okay? So what is this thing? So actually there's many power series that satisfy this, and one of them is this one, f of t. So I'll write it down as a limit, which is going to converge in this funny ring, of 1 plus t to the 1 over p to the n to the power of p to the n. Okay. So this limit, you have to check, and it's not very difficult, that this limit converges inside of this ring right here. And once you've done that, this property is formal. I mean, imagine taking this limit and substituting t to the p for t, and that has the effect of decreasing this n by 1. Do the change of variable, n goes to n plus 1, that increases this n, and then you pull out a power of p, and there you go. So it's this kind of neat thing that exists only in this non-noetherian ring. And by the way, what's the maximal ideal of this ring? It's the thing generated by p, t1 over p, t1 over p squared, and so forth. You really need infinitely many generators. So there's a non-finitely generated ideal for you, okay? So in this sense, this is like the p-adic analog of that solenoid from the previous slide. All right. So the kind of main point of the whole thing, the thesis, is that whatever y of p infinity is, it admits a surprisingly nice description. at least description, at least analytically locally, at least locally analytically. So I'll analytically, and I'll explain what that means presently. All right. Okay, so far so good. So now I'd better talk about modular curves, and I'm just going to kind of start where Frank left off in the last talk. So you attach a modular curve to an arithmetic subgroup of SLN, SL2Z. So let's let gamma be a subgroup of SL2Z, and I mean for this to be an arithmetic subgroup. And the example I'd like you to keep in mind is the principal congruent subgroup gamma of n. So that's matrices congruent to 1 modulo n, right? And we want to define something like y of n, or y of gamma, over C, over various rings, but kind of in order of decreasing level of, or increasing level of difficulty. So over the complex numbers, this is no problem whatsoever. This is just the upper half plane modulo gamma of n, although I'm actually going to explain to you in a little bit why this is a little bit of a lie. Over Q, well, Frank explained a little bit how to construct a modular curve over Q, and you see it solves this moduli problem, which if you believe is representable, gives you this curve. Now y of n over Q, it classifies elliptic curves together with a basis for the n torsion, right? So this is kind of not too hard to define. Using the moduli interpretation of y of n. But then there's y of n over z, and this is actually far more difficult. So this is tricky at those primes dividing n. Well, that comes as no surprise, right? The primes dividing n are going to give you some headache. What ends up happening is that, so I mean, as Frank explained, if you have a modular curve of level n at primes not dividing n, that thing should have non-singular reduction. You can reduce it mod p, and the thing will be non-singular. If p does divide the level, then yeah, you do expect some bad reduction. So the first example of this, of bad reduction, well, this is the situation of Deligne-Rappaport. Okay, so I'm going to draw you this famous picture. So let's consider y naught of p, the modular curve for gamma naught of p, right? And I'm going to consider this as lying over spec zp, right? So just kind of change the base to zp, because all I'm interested in is how the thing reduces mod p. Now, you should think of this thing as kind of arithmetic surface, right? It's this scheme of dimension 2. And one of the directions is the spec zp direction. So I'm going to attempt to draw this. So how do you draw spec zp? It's got 2 points. So it's got like one big point, like one little point. There it is, okay. Okay. All right, so this is like, how am I doing here? Is that too far down? No, it's okay. Here's spec qp, that's like the big point. And the fiber of y naught of p over spec qp is this non-singular thing, because we're in characteristic 0. So how do I draw a non-singular curve? I don't really know. I mean, something like this. I don't know, whatever. It's not supposed to cross. I made a mistake right there. It's not supposed to cross itself. Okay. That's okay. But the exciting part is the special fiber, of course. So over spec fp, you get this cool picture that's like a DNA strand, like this. So it's like a double helix. There are 2 strands, and each of them is isomorphic to y of 1 over fp. So basically 2 affine lines which cross. Now y of 1 classifies elliptic curves, so which elliptic curves are they crossing at? They're crossing at the supersingular curves. So the singularities at supersingular So that's what I have to say about the Deligne-Rappaport model for y naught of p, with the additional piece of information that these crossings are very well behaved They're like normal crossings of multiplicity 1. So they're rather well behaved as singularities go. Okay. All right. So that's actually a very important picture to study if you want to study the proof of Ribot's level lowering theorem, because he uses that picture to give a description of the reduction of the Nerone model of the Jacobian of this curve. Okay. So a little bit less well known is the situation where you allow a lot of powers of the prime to divide the level. So what happens then? So the construction of the curves in that case is due to Katz-Maser. Oh no. And the story is, so let's consider y of p to the n, and let's consider this as a scheme over spec zp. And so this is an informal discussion for now. I'm going to explain what y of p to the n is in just a moment. But if I were to draw this same picture, okay, right. So there's the special fiber and there's the generic one. And again, it's something, and then, but the special fiber is going to be very horrible. It's going to have lots of singularities. So here's one strand. You know, I'm doing the best I can to make these singularities seem very bad. And here's some other strand, and here's some other strand. Well, as you can see, it's just a mess. So again, the strands are like, well, no, they're not. But the strands are at least non-singular curves, but they meet again at the supersingular points. And the singularities are quite horrible. But from our point of view, the singularities are what we want to study. So even though they're quite horrible, they're kind of the main attraction here. All right. So now I have to explain to you what Katz-Maser actually did. So the following is going to be a rather crash course in Katz-Maser. So yes, why don't I just put this here for a moment? Beautiful picture that I've drawn here. Okay. So these are the, let me just talk about the moduli problem. I'll just talk about gamma of n, the moduli problem. So informally speaking, what is a gamma of n structure? So the informal story is this. Let's suppose we have an elliptic curve over some base scheme S. A gamma of n structure is a basis P comma Q for the n torsion in the elliptic curve with values in S. So P and Q kind of have to have coordinates in S, so to speak. And this is the kind of provisional definition that's totally fine if n is invertible on S, a condition which I will abbreviate as 1 over n lies in OS. So if n, the integer n, is invertible on your scheme S, there is no problem in defining a gamma of n level structure this way. Things turn out okay. But let me tell you just how bad it is otherwise. So, and let's just say E is an elliptic curve over FP bar, why not? And let's say n equals P, which is obviously not invertible over that base. Then the problem with this definition is that when you take the P torsion in E and consider its points over FP, so this is an FP vector space, right? So it's never going to be 2. It's only going to be 0 or 1. So it's going to be 0 if E is super singular. And 1 if E is ordinary. And in particular, it is never going to be 2. And therefore, this is a terrible definition for schemes on which P is not invertible, because you could never have a gamma of P structure on an elliptic curve over FP bar. So this is not the way that you should be defining a modular curve of level n in the situation where this base scheme n is not invertible. So what can you do? So Katz and Maser treat it very delicately. The basic idea goes back to Drinfeld. So the right definition of a gamma of n structure on an elliptic curve over a scheme S. So it's, again, basically a pair of points. I'm going to phrase it this way. It'll be a group homomorphism, V, from Z modulo NZ squared over to En of S. And this is basically the same thing as saying you've got a pair of points, a P and a Q, right? This has a standard basis vector, so maybe P and Q are just the images of those. Such that, well, this condition is phrased in terms of Cartier divisors on E. So on the one hand, we've got E of N. This is considered as a subscheme of E, and it's a subscheme of E of codimension 1 is like a Cartier divisor. It's an effective Cartier divisor. And this thing is supposed to equal the sum of phi of A comma B, where A and B range through Z mod NZ. And if you haven't brushed up on your hartshorn, that's okay. I'm not really going to be revisiting this definition. The whole point I want to make is that there is a way to patch up the definition of a gamma of N structure on an elliptic curve over a scheme on which N is not invertible. One thing is that this definition takes care of multiplicities. This E of N isn't really the same thing as the physical points of it over S. This might have multiplicities. And right, so for instance, in that rather bad situation where E was over FP and this was a super singular elliptic curve, and I wanted to find a level structure, a gamma of P level structure, well, it would have to be a map from Z mod PZ squared to E of P over FP bar, but that's just 0. It would have to be 0. And in fact, 0 is a perfectly good gamma of P level structure on a supersingular elliptic curve over FP bar. If E is ordinary, on the other hand, this won't be 0, and then this thing will have to be surjective at least. Okay, so you can patch up the notion of a level structure over schemes on which N is not invertible. Okay. So Katz and Mazur pose the following moduli problem, which allows them to define the modular curves over Z, essentially. So they have the following representability theorem. So let's say, I just want to quote some kind of special case of it. So let's say P is a prime, and let's say N is some kind of auxiliary integer, which I declare to be at least 5. And I want this to be prime to P. And I'm going to consider the following moduli problem. Well, it's going to take a scheme S, and it's going to associate to it some data. So the data is going to be the set of triples. Well, the first thing is an elliptic curve E over S, right? The second thing is going to be a gamma of P to the N level structure. And then the third thing is going to be a gamma 1 of N level structure. And I didn't actually define what that was, but if you believe that you can patch up the definition of a gamma of N level structure, then maybe you can believe it for a gamma 1 of N level structure as well. So it's possible to do this. And the theorem of Katz-Mazur covers this case. So, and it produces for us, so the theorem is that this moduli problem is representable. So this is a functor from schemes to sets, and this is representable by a regular scheme and all right, the thing that you would call this is Y of a certain congruent subgroup of SL2Z, And because there's both a p to the n level structure and a gamma 1 of n level structure, I might call it something like gamma of p to the n intersect gamma 1 of n, right? If you make the group smaller, then you kind of add more moduli structure to the elliptic curves. Okay. So, okay, but this is a little too cumbersome, so I'm actually going to let the auxiliary integer n fade into the background and just write this as y sub n. Okay, good. So now we're actually talking about a regular scheme here, and I'm generally not going to give so much attention to this n here. The reason that I put that n in there is because if n is not there and this power of a prime is too small, then we run into this issue of fine moduli problems, and the moduli problem that you write down, if this number is too small, may not be representable. So that's sort of the whole reason that n is there. All right, good. The other thing I want to say is that this scheme y sub n is not geometrically connected. So, okay, so there's an issue here. The complex points of this thing is not actually equal to upper half plane modulo that congruence subgroup. I call this thing gamma. Yes, okay. I mean, you'd think that it would be because they seem to be classifying the same things. The only obstruction to this equaling this is that this thing is connected and this thing is not connected. But why isn't this thing connected? So the reason it's not is that when we chose a gamma p to the n level structure, we were also secretly choosing a primitive p to the nth root of unity. Allow me to explain. Okay, so this is all about the Weil pairing, and so this kind of seems like a bit of a tangent. I mean, who cares if the thing is connected or not? Just pass to the connected component. But actually, the Weil pairing, as we move on through the course, will kind of slowly move front and center. So for any E over S, for any elliptic curve over any base scheme whatsoever, we always have a pairing. Well, yeah, you can look at this in Silverman's book on elliptic curves. So at least for some contexts you get this. What I really need, though, is that you want a pairing of group schemes. U p to the n. Okay, so e p to n cross e p to the n into mu p to the n. So if you study elliptic curves, one of the things that you know about them is that their torsion is sort of auto-dual, right? So e p to the n, another way of saying this, e p to the n is its own Cartier dual, and the duality is expressed by this Weil pairing. Okay. So if, let's suppose phi is a gamma of p to the n level structure, on E over S. So let me recall that this gamma was supposed to be like a map from z p to the n squared into the p to the n torsion on E points over S. Then you can use this Weil pairing to do the following thing. I mean, I can take the kind of point P and the point Q, right, by evaluating phi on the two standard basis vectors for z mod p to the n squared, and I can Weil pair them together and get something in mu pn to the s. So whenever I've got a gamma p to the n level structure on an elliptic curve over whatever base scheme, I automatically get a p to the nth root of unity. So let me just recall what this y of n was supposed to do for us. This is the moduli space of elliptic curves with a p to the n level structure and this auxiliary gamma 1 of n structure, which I don't really care about so much. Then because this classifies elliptic curves together with the p to the n level structure, the above tells me I get a point of mu p to the n. So I get a morphism like so. So whatever I get here, I mean, this is a scheme fibered over mu p to the n. What is mu p to the n? I mean, as a scheme, it's like, well, yeah, I can define what it is, but what I'd like to do is just say, when you pass to a ring of integers in a cyclotomic field, the thing breaks up into pieces. So let's say you've got K to be the p to the nth cyclotomic field. What I can do is say, like, yn, let me base change it to OK. Oh, I don't even need this p there. I don't know what it's doing there. I can do this perfectly well over the number field K. Okay. So I can base change to OK, to that number field, to that the ring of integers in that cyclotomic field. And, well, that maps to mu p to the n of OK. But that thing has actual roots of unity in it. So let me just take the subscheme of this to be the preimage of that thing. So over OK, this has a primitive p to the nth root of unity. So I let yn zeta just be the preimage of that. And that's going to be a geometrically connected component of yn. And now I can go over here and just revise and say h mod gamma is the same as yn zeta of c, where zeta is e to the 2 pi I over e to the n. So the h mod gamma interpretation just gives you one connected component. Okay. All right. Very nice. All right, so what have I done? I've defined the basic moduli problem. We know what yn is. We know that it has different geometrically connected components. And now I have to explain to you why its special fiber, when you look at it mod p, it looks like this kind of has all these strands to it. Why does it have all of those different irreducible components? Well, this is explained by the tendency of elliptic curves mod p to not have all of their torsion points be physical points. So this next slide describes what is the special fiber of yn zeta considered as a scheme over zp zeta p to the n. Maybe I should decorate this with a p to the n. Right? So I'm usually interested in the arithmetic locally at p, so kind of from now on all of our schemes are going to be over a p-adic ring. Rather than the integers, zp, rather than the ring of integers in the cyclotomic field, this thing. Okay. So let me briefly sketch why you get all these connected irreducible components. So if you've got an elliptic curve over some base scheme, and that base scheme itself resides over fp bar, say, then you get this level structure, so a gamma of p to the n level structure, phi from z mod p to the n squared into e p to the n s. So the thing is that, E may be ordinary or supersingular mod, let's say S is just FP itself, then this is going to just sort of fall short of looking anything like this. It might be 0, and it might be just a line, but the point is this is never injective. The kernel always contains at least a line. And by a line inside of this thing, which is like a plane, a line in the plane would be like a free z mod p to the n submodule of rank 1. So the kernel always contains a line L inside of z mod p to the n squared, right? Okay. And the lines are classified by the projective line over z mod p to the n, right? If I define this thing to be the set of all such free z mod p to the n submodules of this, of rank 1, okay? It's how many elements does it have? P plus 1 times p to the n minus 1, something like this. Then you can go ahead and define a subscheme Yn Fp zeta. Oh, right. Well, okay. So this is the thing we're interested in. And you can express it as a union over all lines in here of a subscheme which, I'll just call it YL. Okay. So I said whenever you've got a gamma p to the n level structure, it doesn't necessarily determine a line, but I can start with the line, and I can say, okay, which p to the n level structures have the kernel containing that line? And since all level structures have to have kernel containing at least one line, this thing has to be the union of these things. So as long as you believe that the condition that the kernel contains the line is like a closed condition, that means that this YL is a closed subscheme of this, and that means that we've expressed the whole modular curve as a union of these subschemes. Okay? Now, how do these subschemes intersect one another? Well, if you had two different lines, and the kernel contained both of them, then that kernel would just have to be everything, because two lines are going to span the whole plane if they're distinct. And when the kernel is everything, well, that's like a supersingular elliptic curve, right? If E is supersingular, then phi is just going to have to be 0, as I explained before. So these subschemes intersect at the supersingular points. Okay. And that's why we've got this nice picture that I drew earlier. If I were to draw Yn zeta over Fp, you would have a strand for each point of that projective line over z mod p to the n. Okay. So that kind of explains why, although it doesn't explain what these strands actually are. So Katz and Mazur do explain what the strands are. They're called Degussa curves. And they're not going to be so important for our lectures, but I'd like to say that they're somewhat well understood. They classify elliptic curves over a scheme of characteristic P together with something like a level structure, something like a point of order n. And that point of order n always has to be 0 in the supersingular case, so kind of why they have to intersect like this. Okay. All right, so this is a good, nice picture of what the reduction of a modular curve is when that curve has level P to the n and it's mod P. It's this irreducible thing, and I don't think I drew these singularities to be quite nasty enough. Okay. I mean, the intersection, okay. Those intersections, I mean, they're going to be multiplicities like crazy, so non-reduced, all this stuff. Okay. So it's these it's these singularities that we're really interested in. And I mean, in the end, it's sort of like there's a disclaimer. I'm not going to describe what the modular curve at infinite level is in its entirety, but rather only in a neighborhood of a point. A point like this, or maybe a point like this. That would be the very interesting thing to do. So I'm interested in the local structure of these guys, and especially at their singularities. So how do we study a singularity of a curve over a point? Well, what we do is we take the completed local ring. So a completed local ring is something that measures the nature of a singularity. So I want to do the following thing. So let's say when you have a modular curve y of gamma, I'm going to consider all of these things over, well, ZP is fine, but actually, ZP, the residue field is FP, and I actually want that to be FP bar because I don't really care about whether things are rational over FP or not. So actually what I want to do is write down this ring W, and W is supposed to be the ring of Witt vectors over FP bar. Okay, and this is a DVR, and W modulo P is just FP bar. So if you've never seen that construction before, you can just think of W in your head as being ZP. There's nothing really lost in saying that. So here's the thing. Whenever we have a point X in the special fiber, so let's say this is in Y of gamma of FP bar. So this thing represents an elliptic curve together with some level structure, and everything's going on over FP bar. Well, you know, it's a point of the scheme. So you could consider the local ring O of y gamma, comma, x. So these are like, this is the local ring of functions on y of gamma defined in a neighborhood of x. This is something you know you can do. If you have any point of a scheme, that point has a local ring. And since the scheme was noetherian, the local ring is 2. And this has some maximal ideal. Call it mx. And the thing to do now is take the completion. That's the mx adic completion of the local ring, like so, okay. And so this is the thing that kind of measures how bad the singularity of y of gamma is at x. And here are some things that we know. So in the situation where you have, where x is like a non-singular point, which is to say, if x is ordinary, or if p doesn't divide the level, so if gamma has prime to p level, then this completed local ring is really just a power series ring. So it's like taking an affine line and completing it at the maximal ideal considered at a point mod p. And what you do when you get that is you just get a dumb power series ring. So this is supposed to look like W double brackets t. So t is just going to be any uniformizing parameter for y of gamma at x. And then since you're in a non-singular situation, the completion is just a power series ring. Okay, so that's sort of the boring case. So the interesting case happens when you've got bad reduction, and then this completed local ring is going to tell you something interesting about what that singularity looks like. So here's the one example I know how to write down. So in the Deligne-Rappaport situation, well, remember what that looked like. They looked like a nice pair of DNA strands like this, the double helix. And look right here. So maybe x is this point. It's one of the super singular elliptic curves mod p. And in an analytic neighborhood of that point, you see two strands intersecting. It sort of just looks like a pair of axes. So mod p, the thing should really have equation xy equals 0. And that's exactly what happens. So the local ring of y naught of p at x, when you complete it, just looks like this. W, double brackets, it's a capital X, capital Y, modulo x, y equals p. Okay. So what's going on here? So first of all, this is a regular local ring. Remember what regular local ring means. I mean, maximal ideal mod maximal ideal squared. The dimension of that over the residue field should be the same thing as the dimension of the whole ring. If I call the thing A, that should be A. The dimension of all these guys is 2, right? It's 2, right? I mean, there's a p direction and then there's like an x, it's like an x direction. So, so you can check that this condition holds in this situation. Whereas, you know, if I put a p squared here, it wouldn't hold so well. So go ahead and do that. You know, check that this really is a regular local ring. And then modulo p, what do you get? You get, you get fp bar double brackets xy mod xy. And that's going to give you, like an analytically speaking, a pair of axes. It's like a close-up of the origin in a pair of axes. All right, so obviously the next thing to do would be to consider modular curves of level like gamma of p to the n, right? And so here we go. All right, O hat of yn x is isomorphic. I have no idea. I mean, big question marks all around. So as far as I know, I mean, it's still a regular local ring of dimension 2. And as far as I know, there's no algorithm to compute a presentation of this thing when n is at all big, like at least 2. And what would that mean? I mean, like, to within a degree of accuracy, can you come up with an algorithm that kind of spits out generators and relations for this regular local ring? I have no idea how to do that. And this is a very interesting regular local ring. I mean, it's got a lot of symmetries to it. The thing has an action of the group GL2Z mod P to the N Z. Because you can take a level structure, it's like a P and a Q, and you can use a matrix with coefficients in Z mod P to the NZ, and you can get a new level structure just by operating on that basis. So it's a very symmetric thing to be considering, and yet we don't know what it is. And, well, you may say, okay, well, what about this thing with connected components? So, I mean, this thing is kind of, when you pass to this ring containing P to the nth roots of unity, the thing splits up. Maybe the individual components are simpler. So, okay, yn zeta x. Maybe do the same thing with a zeta there, and this thing has an action, no longer of GL2, but of SL2. As far as the Weyl pairing is concerned, an element of GL2 Z mod P to the NZ acts on the Weyl pairing through the determinant map. And if you want to fix the Weyl pairing, I mean zeta has to map to zeta, the thing has to have determinant 1. Fine. So it's still a regular local ring, it's still very symmetric, and I still have no idea what it is. Very good. All right. So I don't really know when to stop, so I'll just have, I just have one more. Yeah, okay, I just have one more page of notes. That's very good. All right. So the remedy of this situation is actually to do the very weird thing of passing to the infinite level. So here is the idea. Let us choose compatible systems Well, first, let me take a pth root of unity, a p squared root of unity. These are all supposed to be primitive pth power roots of unity. And I'm going to call the whole system zeta. And so what I mean by compatible, these are supposed to be compatible in the sense that the pth power of this is this, the pth power of this is this, and so forth. The whole system I'm just going to call zeta. Okay. And we've also got these modular curves. We've got y1, zeta p. Oh, no, y2, zeta p squared, y3, zeta p cubed, and so forth. And somehow, the whole inverse system of them I'll just call y infinity zeta. And now I choose points in this special fiber. So let's say x1 is a point here, x2 is a point here, and these points are all compatible, ... And all of the system of those points I just call x, and x is somehow a point in the special fiber of y infinity, the modular curve at an infinite level. So this is just formal what I'm doing here. And when I do this, I mean, the singularities, I mean, here's a gamma naught of p, but as you add more and more level structure, the singularity gets worse and worse, and it would appear that the regular local rings you get just get weirder and weirder and more complex. But when you pass to the infinite level, well, let me just explain what it means to do that. So let's let, okay, so I mean, we've got this nice system here. So here's O, y1 zeta, x1 hat. Okay. So this curve maps to this curve, and whenever you've got one scheme mapping to another, you've got a map of local rings in the other direction. And that map, is a map of local rings, so it extends to the completion, because it's a continuous map. So I can do, I guess this was supposed to be zeta p, huh? Okay, and that's zeta p squared. x2, there's x's everywhere. No, what'd I do? It's not okay? Oh God. No, yeah. See, I'm explaining that I just explain the arrows going the other direction, but my visual system just sees this and it wants to just, okay, thank you for being such attentive audience members, thank you. So we get a forward system of local rings. And I want to jam them all together. So I'm going to just define, I'm going to make the following definition. O hat y infinity zeta, comma x. So this should be the completion of the union, just kind of like what I did before with the p-adic solenoid thing, the completion of the union of all of these rings with respect to, oh, I don't know, mx1, the maximal ideal of this guy. Or I guess you could choose the maximal ideal of this guy. It won't matter. They all define the same topology on that union you can check. That's going to be a consequence of the fact that all of these guys are finite maps. Okay. So it's a huge ring. It's certainly not Noetherian. And it has an action of SL2ZP, a rather large group. Okay. So certainly I can do this, and it's an ad hoc definition. I haven't really defined what y infinity is in the first place, and I actually never will. I mean, in this lecture. This lecture. One day. Just don't get any ideas that I'm going to say, like, this is what y infinity is. I'm not going to do that. We'll have to wait. So, okay. All right. So, I mean, if you'll permit, I sort of don't remember when I started, but I'll just kind of finish what I have to say. So, all right. So first of all, where do these things live? So, I had to kind of extend the base ring to ZP adjoin a primitive p to the nth root of unity to get this. So I kind of have to first do the same thing with the base rings. So why don't I just do this? Let me let OK oh, they're supposed to be W's. Oh boy. Oh well. W. Oh well, W's all around. All right, why don't I take W, adjoin a p to the infinity root of unity, and then complete the result, okay? So whatever this completion is, since the nth stage here contains the nth stage here, completion should really contain OK. So it's going to be an OK algebra. All right. So in the lectures, we're going to discuss the following theorem. Okay, with all of this stuff in place, we can actually give a description of what this local ring is. It depends on whether X is ordinary or supersingular. So if X is ordinary, then this completed local ring thing is isomorphic to OK, double brackets, one variable, t 1 over p infinity. So somehow you took a limit of things which were just, remember, if you're an ordinary point on the modular curve mod p, these completions are just power series rings in one variable. And the maps between them, well, they're weird, but somehow in the limit, maybe it's not too surprising that you would just get some kind of power series ring in one variable, even if it's not Noetherian. Okay. The really interesting thing happens when X is supersingular. Then this completed local ring, y infinity zeta x, winds up being something slightly more complicated. So it's going to be a quotient of a power series ring like this in two variables. Okay, modulo some relation. And that relation, well, you have to mod out by an ideal which is not finally generated again. So here's that ideal. Delta x, y. All right, this is supposed to equal zeta p to the r. Okay, so it's going to be an ideal of that shape. So you have to think of this as kind of a power series ring in two variables modulo one relation, except it's not really like that because the powers have arbitrary p roots. Sorry, the variables have arbitrary p roots, and you kind of have to keep modding out by, you want in this ring this thing to be equal to this thing, but also the pth roots have to equal the pth roots each time. Okay, so that's great. I have to just now explain what this delta is. Where delta is some, well, actually it has ZP coefficient, so that's fine. It's in here. Is a certain explicit power series in two variables. Which satisfies the following properties. Well, I'm just going to list some of those properties. One of them is this one. When you plug in x to the p and y to the p inside of delta, it pops out like this, but there's a sign, so that's weird. When you plug in y to the p squared, that just pops out as 1 power of p, which is very strange also. Okay. And then when you switch the order of y and x, you get a minus sign. So somehow delta is like a weird alternating thing. It turns pth powers into negative pth, well, okay. So I have to give you a context for all of this, obviously, and that's going to be the content of the lectures that will follow. I guess I should say that this isomorphism here, to say something about this theorem, so there's a preprint of mine in which something like this appears, and that preprint exists in some final form, but it's not peer-reviewed, so there's that disclaimer. And then also, the people in project B are going to tell you what this delta is and why it has all of these properties. I hope. Yeah. So not to pressure them or anything. And at the very least, we're not quite going to prove this theorem. At the very least, we're going to find a map from here to here, which is saying a lot, right? That there should exist such a map. Okay, good. Okay. Thank you.